In this video, we're going to look at how horizontal and vertical translations are applied to a function. So we're going to start off with the function y equals x squared, which we know is just our basic parabola. And we're going to look at what happens to the function if we just add a 3 to the outside of it, and what happens if you subtract 4 to it outside the function. So the easiest way to take a look at what these different numbers do to our original parabola is to just throw it into Desmos. So quickly throw these 3 into Desmos and let's take a look at what they look like. So after putting into Desmos, this is what we have. This guy in the middle here, this is our original parabola. So this is f of x equals x squared. This guy up here, this is what it looks like when we added 3. And this guy down here is what it looks like when we subtracted 4. So what happened here? Take a look at our original parabola compared to the blue one. All of the points moved up 3 units. So the point 0, 0 moved up to 0, 3. The point 1, 1 moved up to 1, 4. So every single point was moved up 3. Let's take a look at the green one. The green one had a -4 here. And what happened is every single point of the original parabola, the red one, got shifted down 4 units. So here now this is the point 0, -4. It was 1, 1. Now it's the point 1, 3. So every point moved up 3 when we added a number and moved down 4 when we subtracted that number. So let's summarize that. So if we call this number that's added or subtracted to x squared, if we call it c, then when c is bigger than 0, so when we have a number that's bigger than 0 that's being added to the function, it's going to shift the parabola up. And when c is negative, so when we have a negative number adding to the outside of this parabola, it moved the parabola down. Now let's see what happens when we add and subtract numbers inside the function. So you can compare it to this guy. This plus 3 would be considered outside the function because it's outside of the squared. Here it's inside of the squared touching the x. So what's going to happen to our parabola if we add and subtract numbers inside the function? So go to Desmos and check. So if you tried it in Desmos, this is what you're going to get. Here is our original function. So there's our y equals x squared. The green one, actually let's talk about the blue one first. The blue one here is this guy here. What happens if you add 3? And this green guy here is this function right here. What happened when we subtracted 4 inside the function. So let's see what actually happened here. So this blue guy here, when we added 3 inside the function, it moved the function left 3. Every single point got moved left 3. So originally this point is 0, 0. Now it's -3, 0. Originally this point was -1, 1. And now it's -4, 1. So adding 3 inside the function moved it to the left. And similarly, when we subtracted 4 inside the function, it moved it to the right, the original parabola. Every single point got moved to the right 4. So 0, 0 became 4, 0, 1, 1 became 5, 1, etc. So let's summarize this then. So here we talked about, we called the letter that was outside of the function, adding or subtracting, we called it c. Here we're going to call it d, the number that's inside the function. So let's come up with our rules. So when d is greater than 0, what happens? When d is less than 0, what happens? So this gets a little bit confusing because d is defined as whatever is beside a negative sign. So here it's pretty easy to see that d is 4. D is 4 here, right? Because d is whatever's beside a negative, so d is 4. Here D is not beside a negative sign. So let's just rearrange this a little bit just so that we can see what this would be. So this would be x. If I put a negative sign there, then I got to make this -3. And then these are equivalent, right? Because -3 is +3. So back to here. When D is greater than 0, what happens? Which D is greater than 0? This D is -3, this D is 4. This one's actually greater than 0, but I'm going to make a little note that when D is greater than 0, but it's going to D looks negative. We don't really need to know the exact value of D. The most important thing is, do you know where this problem is going to go? So if this confuses you and you just want to use these when D looks negative, then let's use that. So when D looks negative, where did it actually go? It went to the right. So it's opposite how we think it's going to go. When D looks negative, it moves to the right. Now, actually, in reality, we know it's actually positive because D is defined as whatever's beside that negative sign. So, right, positive D, we're going to the right, but it's going to look negative. So, we're going to more likely refer to the fact that it looks negative, and we're going to go opposite of it because it's easier to remember. Taking a look here, when our D was negative, so our D was -3 here, we went to the left. Now let's put a little note in here that D is going to look positive. Looks positive. And let's just make sure we understand this. So when D looks positive like it is here, we're going to the left 4. Or sorry, I just realized that I made a mistake. It was never left 3. It was always left, sorry, it was never left 4. It was always left 3. Okay, so when D looks positive, it actually goes to the left, and when D looks negative, it actually goes to the right. So now we have these two transformations. We know what happens when we add and subtract numbers to the outside of the function. It moves it up and down. We know what happens when we add and subtract numbers inside the function. It moves it left and right. For the numbers that are added on the outside, everything's just normal. When it looks positive, it goes up. When it looks negative, it goes down. Anything that's added or subtracted inside the function beside the x is opposite. When it looks negative, it actually goes to the right, like what it did here. When it looks positive, it actually goes to the left, like it did here. Now we can apply this to any function. So if we take a look at this notation, this is if you take any function. So here where we're using x squared, you could put anything you want in here, even linear. If you take any function and add a number to it, it's going to move the function up and down in the same way that it did the parabola. If this number is positive, it's going to go up. If it's negative, it's going to go down. Here is what happens if we add and subtract a D value to any function. So instead of having a squared, because we're talking about a parabola, we just have regular function notation. So for any function that we add or subtract a D value to, so a number that's inside the function beside the x, it's going to move it left and right. And when it looks negative, we're going to the right. And when it looks positive, we're going to the left. Now, we know that we could actually take out the D from the negative, and it's going to follow these rules, but it might be more helpful to just talk about what it looks like. When it looks negative, it's going to the right. When it looks positive, it's going to the left. So let's practice not sketching it, but developing our steps for sketching these guys here. So we have different functions than what we just worked with. We just worked with parabolas. Now we're dealing with other functions here. So what is going on? So first of all, let's write out what our parent function is, what our original function is. So above, we always started with y equals x squared. Now, so that was our parent function. Now what is our original function? Our original function here is a square root function. So first, we would sketch out our parent graph. Next, we got to figure out what letter is this one. Is this one C? or is it D? We can always tell if it's C or D depending on if it's inside touching the x or if it's outside the function entirely. So this guy is outside the function because yes, there's an x right beside it, but this is a little square root that's protecting that x. So this -2 is happening completely outside the function. So that is our C. And if it's outside the function, we know we're shifting up and down. And since our C is negative, we're going down 2. Let's take a look at this guy here. What is our original function? Well, as soon as you see a 1 over x somewhere in there, we know that the parent function is the reciprocal. So our parent function is the reciprocal function, 1 over x. What are these numbers right here? So this plus 3 is inside where the x is, literally inside the function, underneath the 1 over, beside the x. So that must be our D. And this plus 8 is outside the function, so it's not involved in this fraction at all, so that must be our C. So now all we have to do is follow our rules for C and D. So let's do with D first. D looks positive. D looks positive. So we're going to the left. We're going to move this to the left 3. Now how about this guy over here? This guy's outside of the function. It's not involved in the division. It's not right beside the axis. Here it's just sitting outside. So that's our C value. Which means that we must be going up 8. So to sketch this function, we would have to sketch our parent function first, and then move every point left 3, and then up 8. Let's try this last one, but try it on your own. Try to list out what the parent function is and the horizontal and vertical shifts. So pause the video and come up with that on your own. If you're back at the video, you are checking your answer. And here's what you should have got. The parent function is the absolute value function. We have a horizontal shift 5 to the right because there is our D value because it's inside the function. And then here's our, D value, and this is our C value because it's outside the function. And so then we have a vertical shift down 1. Let's actually try sketching these things now. So we're going to create the same list that we just did, and we're just going to apply those things. So we know that we're going to start off with the parent function, which is f of x equals this absolute value of x. So we're going to start off with this guy. And then we are going to work on our transformations. So we know that this guy is our D value. It's inside where the x is. Whoops. We've got this guy here is our C value. It's outside of the function. So that means that we are going to the left. Sorry, we're not going to the left. We're going to the right 2. Right 2, and we're going down 4. Right 2, down 4. That's what we've got to do. So let's start with drawing out the absolute value function. So we have to get really fast at drawing out these functions, like really fast, so that we can just do very quickly. Done. Let's connect them all. Here's what the function is going to look like. I'm going to put arrows at the end. And now all I have to do is take these points and move them right 2 and down 4. Right 2 and down 4. So I'll start with this guy here. We're going to go right 2 and down 1, 2, 3, 4. So again, I'm going to show you. We're going 2 spaces to the right and down 4. 1, 2, 3, 4, and then we're going to put a dot there. And we're going to do that for every single point. We're going to do it for this point, right 2, down 1, 2, 3, 4, and we're going to put a dot there. And every other point we're going to do that for, and we're going to get this once we move everything. So we're going to connect it all, and we are done. The final thing that we're going to do is we're going to label. So whenever you have multiple graphs, you just have to label them. So this guy here, that was just f of x equals absolute value of x. And this one was our final function. This was f of x is equal to the absolute value of x minus 2, all minus 4. The final question was asking, what's the domain and range of this thing, of this final function? So let's take a look at the domain. Domain of any absolute value function is like a parabola. It's going to be x is an element of R. X can be 0, 1, 2, 3, 4, and so on and so on. It can also be -1, -2. This is going to keep going, right? So it can be -3, -4, etc., etc. So our domain is x is an element of all real numbers. And our range, what can y be? Y can be anything up here, anything up here. It stops existing at -4. Y is not going to exist down here because we know this absolute value function just turns around there and doesn't come back. So we're going to say that y is an element of all real numbers. Y can be any tiny little number such that y is greater than or equal to -4. And we're done. All right, let's try this one here. Again, following the same process. First, we're starting with the parent function. What is the parent function here? Well, I see a square root here, so the parent function must be the square root of x. Then we have these guys here, this 4 and this 3. We know this one's inside the function, so it must be D. This one's outside, it must be C. So let's write our little to-dos. That must mean we're going 4 units to the left, so we're going left 4 units. And we are going down 3 units. All right, so let's do this. Now that we have this done, you try sketching this. So quickly sketch out the square root function and then move everything left 4 and down 3. Go for it. Pause the video and try it. All right, if you're back at the video, you have sketched this function or attempted to. Firstly, did you start with the square root function? We know if we put a 0 in there, we would get 0, 0, 1, 1, because square root of 1 is 1, and then 4, 2. Those are the 3 easiest points to sketch. And then if you moved every single point, left 4, down 3, this is where you should be. The start of it should be at the point -4, 3, and then there should be a point here, and it's going to intersect the x-axis at negative, or y-axis at -1. And we're done. Last step is domain and range. So I also forgot to label these guys. So this was our original function. And this one was our final function. And now let's do the domain of the final function. So what can x be? Can x be 0? Yes, it can be anything positive, including 0. Can it be -1, -2, -3, -4, -5? It cannot. So x is only going to exist when it is greater or equal to -4. So x is greater than or equal to -4. How about our range? Can y be 0? This eventually will hit 0. It will eventually also hit every positive number. So y can be 0 and anything positive. It can be -1, -2, -3, and after -3 it stops existing. So y has to be greater than or equal to -3. Let's try this last one. This one students find the most confusing because this reciprocal function is a little bit tough to sketch. So first we know that we're starting with the parent function 1 over x, the reciprocal function. And we know this guy down here is our d value because it's in beside the x. This guy up here is our c value. It's outside of the function. So we know we're going to be going to the right 2 units. And we're going up 1 unit. So let's sketch out the original function. So here's where the original points are. Let's just connect them all. We know that there's asymptotes at the x-axis and the y-axis for this guy here. So here is what our original function looks like. Also, when you draw this function, you need to draw the asymptotes because we're going to be shifting those as well. So the key to sketching this guy accurately is to move the asymptotes first. So we know we're going right 2 units and up 1 unit. So let's take this vertical asymptote here. We're going to move it right 2. So we're going to move it from 0 1, 2 right here. And then we're going to move it up 1 unit. But a vertical line moved up 1 unit doesn't change anything. So the only thing that's going to affect this vertical asymptote is moving it to the right 2. So I'm going to just do a new asymptote here at x equals 2. Now let's deal with this asymptote. We're going to move it right 2. Again, not going to affect anything because we're just taking a horizontal line and moving it to the right. Not going to change it. But up 1 unit is going to change it. So we're going to take this horizontal line and move it up 1 unit so that it's at y equals 1. So that it looks like this. And now that we have these boundaries, now we can start plotting the point. So now we're going to take every single point and move it right 2 up 1. Be careful with these points that are at like the 0.5. When we move it right 2, make sure you're doing a full 2 units. So 1 unit would be here, 2 units would be there. So let's move each of these points. Try moving them on your own and then come back to the video once you're done. So here's what it will look like once you've moved all the points. Let's connect them really carefully. So really carefully, and the reason why we're going to do it carefully is we're not going to cross the asymptote. We're not going to cross the asymptote. We're going to have the equations approach the asymptote. Notice that they're not doing this. Whoop! They always have to be going towards the asymptote. Just like this. See how this curve is approaching the asymptote? This one's approaching the asymptote. Same with here and same with here. So they're not going to go whoop in a different direction. This asymptote is like pulling the function towards it. So this is our final solution. So we're just going to label quickly. And now let's come up with our domain and range, and then we'll be done. This is our last example. Okay, so we're just looking at the red guy here. What's the domain of the red guy? Well, just like all other reciprocal functions, x can be everything except for one number where that asymptote is. So before it used to be at 0, but now it's at 2, which means x can be anything, 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 anything except for 2. So we write this like x can be anything, x is an element of all real numbers, but x cannot equal 2. And now for the range. Same, very similar to the domain. Y can be anything, 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 except for the value of the asymptote, which is at 1 in this case. So we're going to say that y is an element of all real numbers, but y cannot equal 1. And we're done.